Audible, audible.
Okay. So, good evening, students. Okay, since people are yet to join, so maybe we can wait for a minute or two. So the others can also join, and then we can start. Screen is visible, right?
Yes, madam. Screen is visible.
Okay. Is there something special today, like any festival or anything? Nothing of that sort, right?
No, madam. No festival. Tomorrow it is there.
Okay, but nobody is joining, so that's why I was a little concerned what happened. Because generally by this time students definitely join, but today nobody is joined. Okay, so maybe we can start slowly. Others will join in the meantime. So I'll formally start the session. Good evening, students. So, welcome to week 4 of live problem solving session for analog circuits course. And I'm Dishadha Devi, a PMRF fellow from IIT Gandhinagar. So, I am audible clearly, right? I'm audible clearly, and my screen is also clearly visible to you, right? My voice is okay. Like, do you want me to talk a little louder, or is this fine? Hello.
It's okay, madam.
Okay. Okay. So maybe let's start. Others will slowly join. So today we'll be discussing problems based on feedbacks and yes. Sorry. Please mute yourself. Okay. So yeah, today we'll be discussing problems based on feedbacks, their impacts, and we'll also discuss phase margin, gain margin, these topics. So starting with the first problem. So in this first problem, in a negative feedback system for a forward gain of A, feedback gain of beta and overall gain, the impact on overall gain compared to open loop system is observed to be the sensitivity is increased by a factor of 1 upon 1 plus A beta due to the fractional change in A. The gain sensitivity is reduced by a factor of 1 plus A beta due to fractional change in A. And same has been repeated in C and D, right? So first of all, there are a few things that we are encountering for the first time, right? So sensitivity is one. So what is the meaning of sensitivity? What do we understand by sensitivity? What is sensitivity? So in general terms, in layman terms, what do you understand by sensitivity? Like, what's your take on sensitivity? We have definitely come across this term in our lives, right? In general. So, what is the meaning of sensitivity? Yes, anyone? Anyone? Do you know what is sensitivity?
Madam, it is a rate of change of output corresponding to changes in the input.
So basically, yeah, that's more in technical terms. But if I talk about layman's, like in layman's language or very in general, sensitivity basically means a small change in something can induce impact in some other factors. So that's when we say, okay, this particular factor, the let's say output is our concern. Okay, so what are the factors in which, when you introduce a small change, you see the change in output, and how much is that change? So that is measured by sensitivity. Okay, so it's basically how sensitive. So if we say a factor is very sensitive with respect to your output, so that means that particular factor, like small changes in that factor will introduce a significant change in your output. So that is the basic idea. So it also shows like which are the important factors that needs to be uh, kept in mind or understood carefully, or handled very carefully based on sensitivity. So if the sensitivity is, like, if it is high, that means the factor is very important for us. If the sensitivity is low, it's not of that much importance. So um that is the significance of sensitivity. Now, when we are talking about gain sensitivity, so with respect to, now here we have to discuss it with respect to A. So when we talk about overall gain with negative feedback, so our overall gain looks like A upon 1 plus A beta, correct? So here what we are considering is, let's consider that beta is somewhat constant, some constant, and the independent parameter over here is gain A, and we will see its dependence on our overall gain, that is AF. So that means we will calculate the sensitivity of AF with respect to A, right? So how do we do that? So when we are talking about small changes and we want to monitor small changes, the most commonly used method is differentiation. Differentiation, because we know that differentiation means a small change, right? So that's why we go for differentiation. So for sensitivity, the idea is we go for DAF upon DA, right? So considering beta to be constant, what will be my DAF upon DA? It's this, right? Differentiation of like U upon V. So how do we write it? It's VU dash minus UV dash upon V square, correct? So in the similar way, if we write it here, this becomes 1 plus A beta times 1 minus A into beta upon 1 plus A beta whole square, right? So dF upon dA is 1 upon 1 plus A beta whole square. Let us multiply and divide with A on both sides. Because when we say, okay, so let's divide it and then I'll explain why we are doing this. And if I separate it out, like A1 plus A beta into 1 upon 1 plus A beta into 1 by A. So dA is, this whole term will become AF. So this is AF 1 upon 1 plus A beta into 1 by A. So now what we will do is we will shift AF this side and DA on the other side. So it's DAF upon AF equal to 1 upon 1 plus A beta dA upon A. So this is actually talking about sensitivity. So this is the factor of sensitivity. With respect to this, so we can say A is independent variable. AF is dependent variable. So we are finding the sensitivity of a dependent variable with respect to definitely an independent variable, and by what factor it is actually sensitive. So this is the factor of sensitivity, right? So the value will come from here. So now if we move back to the question was ki, how the gain sensitivity is changing by what factor due to fractional change in A, correct? So how is it changing? It is actually reduced by a factor of 1 plus A beta, correct? So if I say DAF upon AF equal to DA upon A. So now this basically shows the 100% dependence, correct? Because the factor over here is 1. Now when the factor is DAF upon AF is 1 upon A beta plus 1 dA by A. So this particular factor is definitely less than 1, right? So the sensitivity has reduced by a factor of 1 plus A beta. Correct? Did you understand?
Yes,
So
ma'am.
basically the sensitivity is like dx upon x. The change in x with respect to x is sensitivity. But you will define sensitivity with respect to some other factor, right? So some dependent parameter or some dependent variable, how it is changing with respect to an independent variable. So which you have control over. So that is the idea. Okay. So moving on to the second problem. So in this second problem, again we have a negative feedback amplifier with closed loop gain closed loop gain is 100 and open loop gain is 10 to the power 4. So first of all, we need to find the value of beta, right? And then the second part of the same problem is, like, consider that A is, so this is A. So we can directly maybe write A. If A changes to 10 to the power 3, then what will be the new AF? So first we will find this beta, we will substitute this beta over here, and then using A and beta, we will find the new gain. That is the flow. So we know that closed loop gain is A upon 1 plus A beta, correct? For negative feedback. This we all know. So here we know it is 100. Here it is 10 to the power 4 by 1 plus 10 to the power 4 into beta. So maybe 2. 100. So it is 10 to the power 4 beta 99. So beta is 0.0099, correct? Now what we will do, we'll use the same beta here. So beta is 0.0099. And now we have to find AF, that is A upon 1 plus, so A dash maybe, A dash beta. So AF is 10 to the power 3, 1 plus 10 to the power 3 into 0.0099. So how much is the AF that you are getting? Yes, can you quickly calculate? What is the value of AF? How much is AF? Okay, yes, we got the answer. It is 91.743. Correct. AF is 91.743. So very straightforward, right? Only you have to use the formula, nothing much. Okay, so moving on to the next problem. So in this problem, it is asked that if you have a current amplifier with Ri as input resistance and R0 as output resistance, what will be the effect of having a negative feedback for the amplifier on these resistances? So basically, the idea is whenever you have uh, negative feedback, although it reduces the gain, it improves the impedances like output impedance as well as input impedance for all different kind of amplifiers that we have. Okay, so when we say current amplifier, what do we deduce from a current amplifier? If, right, if it is said that you have a current amplifier, then what is the input? What is the output? Okay, if it is a current amplifier, then what will be the input to the circuit? Okay, how many of you know about types of amplifier like current, voltage, transconductance, transresistance? Okay, who doesn't know about this? Maybe can raise your hands. All of you know about the types of amplifiers? Okay. So yeah, maybe you can unmute and respond, right? So it's easier for me to understand. Okay, I'll explain. So based on when we talk about types of amplifier, like amplifiers are categorized in various different ways. Okay, like first is based on inputs, like input and output, from where you get these categories of current, voltage, transconductance, transimpedance amplifiers. These are based on the input and output that you provide to the system. Now, what other types of amplifiers we have? Um, Again, based on devices used, we have BJT based amplifiers. We have MOS based amplifiers. Then, if we talk about device configuration based on um, based on amplifier configuration, I would say so these two are actually interrelated. All of them are interrelated. It's just that we are bifurcating them for an easier understanding. Okay. So when we have a BJT based amplifier and we talk about amplifier configuration, so it is basically to which terminal of BJT you are giving your input to, and from which terminal you're extracting the output from a BJT or MOS. Depending on that, the configuration of your amplifier changes. So in case of BJT based amplifiers, we have common collector, common base, common emitter amplifiers. Similarly, in case of MOS, we have common source, common drain amplifiers, common gate, common source, common drain, common gate amplifiers. All these amplifiers have their own characteristics, their own behaviors, their own advantages and disadvantages, and their own applications. Based on them, we use these amplifiers. And another category is of power amplifiers. These are again further classified into class A, class B, class AB, and so on. So these are like if I talk about types of amplifier and if I try to broadly categorize them, then this is somewhat how it will look like, more or less. Okay. So yeah. So here, as you can see, based on input and output, sorry.
Madam, can we classify amplifiers on the basis of frequencies?
Frequency is like
High frequency amplifier, low frequency, medium frequency, or
I mean, you can do that like high frequency. So RF amplifiers, we use them for high frequency. We call them RF amplifiers and all. Frequency is also one way, but yeah, that is a next level of
okay.
analysis. But yeah, definitely you can say like high frequency, mid range frequency, and low frequency amplifiers, because definitely based on what circuit you design, your frequency profile will be. So your frequency response will look like that. And based on like a flat gain range, like where you get a constant gain, in that range of frequencies only you would use your amplifier, correct?
Ma'am,
So,
ma'am,
yes.
op amp is high frequency or medium range frequency amplifier? Op amp 741.
OPAMP 741 can be used for like it can give you a good amount of frequencies, and most of the time the frequency profile is somewhat like this. So this is gain. For very low frequencies, sometimes you will see a certain drop, but it has mid-range frequency, and then higher frequencies go like for higher frequencies again the gain rolls off. So, but more or less you can significantly use it for lower frequencies like 110 kilohertz. This range of frequencies like kilohertz may definitely you can use. Few megahertz you can use, and this can be found from the gain bandwidth product. So whichever op-amp or any IC that you are using, so you can follow the you can follow its this, what do we say, like
Data sheet.
yeah, data sheet, definitely data sheet. So in data sheet you will get the values for gain bandwidth product, and gain values will also be there. So from there you can extract the bandwidths, and definitely bandwidths can be changed depending on how we uh, integrate them with RNCs, like external resistors and capacitors, how we are integrating them into our circuit. Based on that, we can slightly tweak our bandwidths. But more or less, if we talk about open loop gain and bandwidth, that can be observed from the data sheet.
Okay, madam. Thank you.
Yeah. So based on frequency also maybe we can categorize it, so that will also be a part. Maybe I can, based on frequencies, it can be a low frequency amplifier, mid-range or mid-range frequencies, high frequencies, then we do have like RF amplifiers. So these come under high frequencies, but definitely what is low, what is high for you, that depends, right? What you might call high might not be a high frequency for somebody else. So that is definitely subjective to change, but more or less these are the categories. Any other thing that comes to mind? Am I missing something? Most of all the categories are covered, right? Anything else that you feel like it's missing?
No, madam.
No, right? Huh. Okay, so the basic idea was we were about to delve into this aspect of uh, amplifiers based on inputs and output. So that is current, transconductance, trans impedance, and voltage amplifiers for this particular problem. So when I say a current amplifier, my input is current, my output is also current, and for any type of amplifier, the figure of merit is output by input. You always want to observe output by input ratio. It is gain in one case, and definitely it would be impedance and conductance in others, as we will observe. So in this particular case, since output is current and input is also current, so output by input would be current gain. So in current amplifier, everything we are dealing with currents. On both the input as well as output port, we are only dealing with currents, right? Now, if it is a voltage amplifier, in a voltage amplifier, similar to current, input would be voltage and output would also be voltage. And output by input is called voltage gain over here, which we are quite familiar with, right? We have been using voltage gain since first assignment. Now, when we talk about trans conductance amplifier, so what is transconductance? Transconductance is current upon voltage, right? So that means input is voltage, output is current, and output by input is your transconductance. And we denote it with the G. So have you ever come across a transconductance amplifier or any device that you can think of where you give input and you get output as current? Your input is voltage and your output is current. Can you think of any device from our electronics? Any device where we give
Maybe
input.
op-amp,
Sorry.
maybe op-amp. No, it is providing output voltage, isn't it?
No, but there definitely you get the current also. So the most basic component of all these op amps and everything is a MOSFET or a BJT, right? So if we talk about a MOSFET, what is the input in a MOSFET? Most of the times, like all the time, it is gate voltage. We give input to gate, right? And what we give in input is voltage. We never give current to a MOSFET. MOSFET cannot, gate cannot take current. So input is voltage over there. And in MOS device, if you know about a MOSFET and it's working, the voltage that you provide to gate actually helps in the current flow, and the output that you get is actually drain current.
Yes, ma'am. Drain current.
Yes.
Yes. So input is voltage over there, and output is current.
Input is
So-
open. It is open. Input
Sorry?
is open. Input is open actually. There is no gate current.
Sorry, so that's what. So input is voltage. That's why you can never have input current in MOSFET, right?
Yes.
And output is drain current.
Drain current. Yes.
So the best example of a transconductance amplifier model is a MOSFET. We observed the small signal model of MOSFET, right? We discussed this small signal model of MOSFET. So here, if you see, it is GM-VGS. And what is this GM? Transconductance.
Transconductance.
And what we are discussing over here is also transconductance amplifier. So basically, if you observe a transconductance amplifier, or like if you draw the circuit of a transconductance amplifier, it will look more or less like this small signal model of a MOSFET. So basically, the small signal model of MOSFET is drawn from the inspiration of small signal model for the MOSFET is from transconductance amplifier model.
Ma'am, can we consider GM as a figure of merit of any transistor for selecting as an amplifier?
Yes, definitely. When we have MOS-based amplifiers, hopefully we will discuss MOS-based amplifiers. So whenever you have MOS-based amplifiers, you define your gain based on GM and R. So GM is very important. Like your GM defines how much current is actually flowing through your circuit, right? How much current you can draw out of your transistor, and which will in response give you the output. So GM is definitely a figure of merit when we use MOSFETs. Okay? Yeah. And definitely you can convert one sort of amplifier to other. So it's like if I am getting output as current, I want output as voltage. What can I do? If a circuit is there, it is giving me output current, but I want to measure output voltage. What can I do?
Current to voltage converter circuit can be used.
Current to voltage circuit क्यों चाहिए? You can always use a load resistor, right? Drop across the load will be
Simplest
the
way
load.
is, okay, yes, madam.
Correct?
Okay. Yes.
Because V equal to IR, Ohm's law is always valid.
Yes.
So for current to voltage conversion, you don't need to use circuits and all, right? You can simply use a load resistor and you can get voltage out of it. That's how in like in MOSFETs, if I want output as voltage, so what I'll do at output terminal, I'll use a load resistor. and whatever voltage is dropping across that load resistor, that is my output voltage, and I'll report the gain as output upon output, that is voltage gain. Correct? But ideally, if I talk about the MOSFET itself, then it is a transconductance amplifier. Like it follows the model of a transconductance amplifier. Is this clear?
Okay, madam. Thank you.
Yeah. So similarly, we have transimpedance. Now, if it is transimpedance, then what would be the input and what will be the output?
Input would be current and output would be voltage.
Yes, input would be current and output would be voltage. So output by input, you will get Z, or most of the time Z is more appropriate because we are talking about impedance. But you can also denote it by R. It depends. And yeah, depending on these, the units will also change. So since it is an impedance, definitely the unit will be ohms. Here it will be Siemens. Whereas voltage gain and current gain are unitless because they are volt by volt and ampere upon ampere. But we generally denote them in dBs. Okay, so these are the units. So now, so this is all about the amplifiers, like current amplifier, voltage amplifier, transconductance, and transresistance. So in this problem, what was the problem? The question was asked that what will happen if you have a current amplifier to input and output resistance when you have negative feedback. So I said that negative feedback will always improve our so this is always true, like yeah, this is always true and applicable. So negative feedback always improves input and output impedances. It improves the bandwidth. Okay, so whenever you have a negative feedback, you can be sure that your input and output resistance is improved. Why I'm not commenting on increased or decreased? Because it will depend on what type of input you are using, right? So whether you are using input as a voltage or current, the behavior of your input resistance would be opposite. Do you understand that? Like how loading effect will be considered for a voltage or a current source circuit? How would we consider voltage loading effect for voltage or current source circuit? Okay, so let's say I have in my input I have voltage, okay, voltage source, and I so what if I have input as my voltage source? What should be my input resistance? Should it be high or low?
Please repeat once.
If I have input as voltage source, input is voltage source. So what about input resistance? Should it be high or low?
High.
Why?
In voltage source, we don't want that the output should the voltage should get degraded in the other parts, and we must get the full output full voltage at the output.
Okay, so if my input is current source, then What about my input impedance, or how do I want my input impedance to be?
Ma'am, 0.
Yeah, so low. So basically the idea is, see, first of all, the things that we need to understand is, for voltage, we go for Thevenin equivalent. Thevenin equivalent circuits. So whatever circuit you have, you try to minimize it into Thevenin equivalent form for voltage sources. Similarly, for current, we go for Norton equivalent circuits. Now, what do I mean by that? So, for voltage source, let's say you have a voltage source, okay, Vs, and it will have some source resistance, say Rs, okay, and then you have your input resistance Rn, okay, and this is where you are observing Vn, right? Similarly, if you have a current source Is, your current source resistance Rs will come in parallel, and similarly your Rn will also come in parallel, and the current flowing through this will be In. So this is Thevenin equivalent. This is Norton equivalent circuits, right? So here you see, I want my Vs to be completely obtained as my Vin. I want my Vin to be almost equal to Vs, and similarly my In to be almost equal to Is. Correct? So for this behavior, if I want my Vin to be almost equal to Vs, then what should be the relation between my Rn and Rs? And similarly here also, what should be the relation between my Rn and Rs? See, for voltage, I want all of my voltage to drop across Rn. That means if Rn as high Rn as possible, if I use as high Rn as possible, I'll get my Vin almost equal to the source. If Rn is open circuited, that means Vs will be completely replicated as Vin. You understand this?
Yes,
Simple
ma'am.
voltage division rule. Now, similarly, if you apply current division, so which path will have higher current? High resistance path or low resistance path? Which path
Low
will have,
resistance part, low resistance path will have higher current because it will not
yes,
stop
low
flowing of current.
resistance. Yes, so low resistance path will always have higher current. That's why short circuit path means zero resistance. So always if there is a short circuit, that means all the current will flow through that short circuit path. Okay. So for that, if I want my In to be almost equal to Is, that means my Rn should be much, much smaller compared to Rs, right? Is this clear?
Yes, ma'am.
So this is for input side, correct? We have observed input side mein what will happen if there is a voltage source and a current source, correct? Now let's see what will happen in output. So now you have come to output side. In output side, let's say you have VO. there is some output resistance of the circuit, and then you have, say, load resistance, okay, RL, and plus minus the voltage across the load resistance is V out, okay. Mind you that this is part of amplifier. This side you have amplifier. Here also, on this side you will have amplifier. Now, when we talk about output side, R0, and this is RL. So, in output side, this side is your amplifier part, and here also this side is your amplifier part, okay. So after this, maybe I'll draw a voltage amplifier or a current amplifier to show like what I mean by these. Like this side is amplifier part, this side is amplifier part. What is basically that I'm talking about? You'll understand in just some moment, some time. Okay. So yeah. So this is our output side. Okay. Now see what I want. My output, so from a voltage perspective, I want my output voltage, whatever voltage I am getting in output from my amplifier, that should completely be observed across my load. Correct? Whatever output I am observing from the amplifier, the output should be appearing across the load. Because from load, I am observing ki what is the output. So in midway, agar the drop across my output resistance of amplifier, that is R0, is higher, that means the actual output that I'm observing across the load is very low. And if I calculate the gain based on that, my gain will also come out to be very low. Correct? So here what I want, my V0 is almost equal to V out. And here I want I0 is almost equal to I out. So what can I do? So I can either increase RL, right? But do I want that my output voltage to be dependent on load? Like say if I am using our 1 kilo ohm load, I get some output voltage. I use a 10 kilo ohm load, I get another output voltage. Use a 1 mega ohm load, I get another output voltage. Do I want that behavior?
No, ma'am, we was independent of load.
Yes, we want it to be independent of load, right? Because so if we want our output to be independent of load, then how can we obtain that? So that can be done like if I reduce my R0 to so like uh, typically to such a small value that whatever load I am applying, like load resistance I am using, or whatever load I am using, its value is always much, much larger than my output impedance or output impedance of my amplifier. Then whatever load I'll use, I will get an independent output, right? With respect to the load. Correct? Did you understand
Yes,
what
ma'am.
I'm saying? So the idea is output should be independent of RL. This has to be kept in mind. So if I want my output to be independent of RL, what I can do, my R0 should be much smaller than RL, such that my output becomes independent of load resistance, right? So this is the
Yes, ma'am.
case when you have output as voltage. Now what will happen if you have output as current? I want all my current to flow through my RL.
R0 should be higher than RL.
Yes. So here my R0 should be as high as possible compared to RL, so that my output current becomes independent of load. Right? Now see, one thing, if you observe, the behavior of input impedance and that of output impedance for same voltage and current sources are different for both input side as well as output side. They are opposite to each other. Do you understand this?
Yes, ma'am.
So now if I let's say I draw a voltage amplifier. So how will a complete voltage amplifier look like? So you will have some source. Okay, this source will have some resistance Rs, and you will have an input impedance Rin. Then,
Rin would be low and RL should be high.
yeah, so here you will have voltage, output voltage, which is gain times input voltage, right? And then you will have load resistance, output impedance, and then you have load resistance. So in this, this whole region is your amplifier. So this is your amplifier, right? So when we are talking about input impedance, we are talking about this Rin, and output impedance, we are talking about this R0. So this is the part of amplifier, the highlighted part. Okay? So that's why I said, right, in output side, see the arrow. R0 ke left mein, it is amplifier. So see, R0 ke left mein, you have amplifier, right? R0 and its left. And similarly, Rin and its right side is the part of amplifier. Getting my point?
Yes, ma'am.
So now we understood how things behave, like what are the ideally requirements for impedances uh, when we have input as voltage and currents, and similarly when we have output as voltages and currents, how things change. And when I said that negative feedback will always improve the input and output impedances, so basically we will so improvement means moving towards the ideality, right? So that is the idea. Now in case of current amplifier, how your Rin and Rout will be, like will it increase or reduce with negative feedback in case of current amplifier? So current amplifier mein, how do you want your Rin to be high or low? In current amplifier, Rin is high or low?
High.
Rin is high. In current amplifier, Rn would be high or low? This is current amplifier, right? Rn is high or low here?
Low. It should be lower than RS.
Yes. Ideally, it should be 0.
0. Ideally.
Ideally, Rn should be 0. Here, ideally, Rn should be infinite. Here, ideally, R0 should be 0. R0 should be infinite. Okay. So yeah. So what was it? Rn should be high or low for current amplifier?
Ideally 0 or low.
Low. So Rn should be low. And what about R out?
R out should be higher.
It should be high. So this is the scenario. Now you had an amplifier, current amplifier with Rn of certain value, R out of certain value. They are definitely low and high respectively. But now by introducing negative feedback, we said we will see improvement, right? So if we will observe improvement, then what should happen? Rn should be increasing or reducing?
Rn 0 and R not infinite.
Yeah, so after negative feedback, this should be further reduced, right? Because we want improvement. Similarly, here after negative feedback, again, this should also improve. So we want increment, right? As approaching ideality, correct? So that's why Rn will be reducing and R0 will be increasing with negative feedback. So did you understand? We discussed a lot of things in this particular problem. Did you get it what we discussed? Any doubts? Because these concepts are very important. These are basic concepts. No matter how complex circuit you would use, at the end, so let's say if you have an amplifier, any advanced amplifier based on op amps and multi-stage op amp, cascade, any op amps or any amplifiers, at the end, the concept boils down to this. That's why it is very important to understand how feedback works, what is the importance of feedback, how should your impedances be in order to obtain optimal results. So these are very important. So any doubts? If you want me to repeat any part, feel free to ask. Is it clear to everyone?
Yes, madam.
Okay. So maybe you can go through the notes as well as lecture once again. Yeah, somebody is saying something. Okay, so you can go through the notes as well as lecture once again and see if you have some doubts, maybe you can bring it up in next session, okay? But there is a lot of things, there are a lot that we have discussed in this particular problem. But I hope you could retain those things because these are very important concepts, okay? And these are bases of your amplifiers. So that's why it is very important to understand these. Okay. Moving on to the next problem. So in this problem, for the circuit shown below, find the exact value of beta A V naught VF for AF equal to 5 volt by volt, VA equal to 1 volt, R2 by R1 is 4.128. Okay. So first of all, what is beta? What is beta? Beta is feedback path gain, right? So in feedback path, this will come in denominator. Like from this side, we are observing the input, and here we will get the output. Okay? So let's say if I write this as VF. So VF by V naught is beta. Do you understand this? Any doubts in this? So this is just feedback path gain, right? Beta. So that's why I wrote it like this. So if from the figure, if I have to write VF upon V out, how would it look like? It is R1 upon R1 plus R2, correct? Simple voltage division. So I can write it like 1 upon 1 plus R2 by R1. This is beta. So this is 1 upon 1 plus 4.128, which will give me the value of beta. So what is the value of beta over here? What is the value of beta?
Point 0.195.
0.195, yes. 0.195. Now you have got beta. You know AF. AF is overall gain, right? So if I ask you what is open loop gain, then how would you find? AF is A upon 1 plus A beta, we all know. AF is already given to be 5. A we don't know, 1 plus A into 0.195. So basically we have to reduce this equation. Okay. So what is the value of A that you're getting?
$200.
Yes. What is the unit? Volt by volt. Pay attention to the units because sometimes gains are given in dBs and you need to convert. So that's why always you should be very careful with units, right? Now, okay, so we have found beta, we have found A. What else was asked? V naught was asked. How do you find V naught? What is V naught? Output voltage is gain times input voltage, right? Simple. So gain you already know it is 5 and output was given as 1 volt, which gives us gain of output voltage of 5 volts. Now if output voltage is of 5 volts, we can calculate VF, right? from here, I can calculate VF. VF is nothing but R1 upon R1 plus R2 into V naught, which is basically VF is beta times V naught. So VF would be 0.195 times 5. What is VF?
4.75.
4.75.
4.75.
75. Okay, so VF is 4.75. 4.75.
Ma'am, 0.975.
0.975, yes. 0.975 volts. Right? Very straightforward. There was nothing complicated or no other concept was required. It's basic calculations. Okay. So moving on to the next problem. Now in this problem again, we have to take reference from this previous circuit. Maybe, so in the previous circuit, yeah, it is asked that if AF, find the change in AF is A is increased by 10%. So now A dash is A plus 10% of A, that is 0.1 A, right? So how much was A? A was 200. So if A is 200, so 1.1 times of 200, how much will be A1?
220.
220. Now if A dash is 220, you simply go for AF dash, that is A dash 1 plus A dash into beta, that is 220 by 1 plus 0.195 into 220. How much is this? How much is AF dash?
And 5.011.
5.011 आ रहा है क्या? Is it 5.011? Anybody else?
Yes, ma'am.
Okay, so if it is 5.011, now since percentage change is given and you have to calculate the percentage change, so what will be the percentage change? It is AF dash minus AF by AF into 100, which is 5.011 minus 5 by 5 times 100. So what is the percentage change? How much is the percentage change that you are observing? Yes, how much is the percentage change?
.22.
0.22%. So this is the percentage change that you're observing in overall gain, right? Okay, so moving on to the next problem. In this problem, you have for open loop transfer function of 1 by s plus 2. So the transfer function is 1 upon s plus 2. Find the phase crossover frequency and gain margin. So what is phase crossover frequency and gain margin? Did we discuss phase crossover frequency before? We discussed gain crossover frequency, right? We didn't discuss phase crossover frequency, if I remember correctly. Okay, so see, as I mentioned, like frequency responses, we have two frequency responses. One with respect to gain, that we call magnitude frequency response. Another is phase response, where you observe the change in phase with respect to frequency. So when we said gain crossover frequency, we said the frequency where your gain crosses 0 dB, that is gain crossover frequency. Like 0 dB gain, as it is important for gain crossover frequency understanding. Similarly, in phase, when your system crosses minus 180 degrees phase, like if it is more negative than minus 180, or the phase goes below 180 degrees in negative, then the system becomes unstable. So that's why phase crossover frequency at phase crossover frequency is the one when phase becomes less than minus 180 degrees. So it crosses minus 180 degrees and it goes even lesser. So let's say if this is your phase and frequency plot, phase, okay, minus 90 degrees, minus 180 degrees, and say here you have minus 270 degrees. And say your phase was going somewhat like this, and at this point it crossed your 180 degrees and it goes lower, then this particular frequency is phase crossover frequency. Okay? Is this clear? So when it goes below minus 180 degrees, we call it phase crossover frequency. And at phase crossover frequency, we will calculate gain margin. At gain crossover frequency, we used to calculate phase margin. In phase crossover frequency, the frequency where your phase is crossing, there you check for gain margin. How much margin is there in gain? Is this okay? Are you with me? Do you get it? Do you understand? So how they are related is at gain crossover frequency, we calculate phase margin. Basically, how much margin in phase you are left with for the system to be stable at this particular frequency. That is the idea. And at phase crossover frequency, we calculate gain margin. Like at phase crossover frequency, so because after this point, due to phase, the system will become unstable. But at that point, how much was the margin in gain that was left? So that is gain margin. So you will calculate gain at that particular frequency, and that is gain margin. Is this clear? Okay. So the idea is we have to calculate this. So for this, first thing that we need to do is we need to write the phase of this particular transfer function. So phase of transfer function, how it will be, there is 1s. So it will correspond to minus 90 degrees minus tan inverse j omega by 2. Correct? And to obtain phase phase crossover frequency, this particular phase needs to be equated to 180 degrees, right? So that means tan inverse j omega by 2 should provide me with 90 degrees. 90 degrees, when would you get 90? That is only possible when omega is infinity. Correct? When omega is infinity, you will get that phase of minus 180 degrees, which is required. So this is the frequency, which is your phase crossover frequency. Now at that particular frequency, you have to calculate the gain. And we observe like how much we are left with to obtain 0 dBs. Like in phase margin, our limit was 180 degrees. So that's why we were saying 180 plus whatever the phase we get, that will give us the phase margin, the limit that we are left with for phase margin. Similarly, when we are calculating gain margin, our limit is 0 dBs. We cannot go below that. So 0 dBs say, now we will compare our gain, whatever gain we are observing. Okay. But clearly at when you put this omega as infinity, when we substitute in the gain, so when we substitute this here, the gain of the transfer function will become 0, right? So when we substitute omega equal to 0, gain of the transfer function becomes 0, and gain margin is 1 by gain margin is 1 by g, or 1 by transfer function at let's write it as phase crossover WPC. So this is WPC, so this is also WPC. So yeah, our limit was, as I mentioned, 0 dB was the limit, right? So 0 dB minus whatever dB that you get, whatever the gain that you get, that will give you phase margin. Sorry, gain margin. So when they are in dBs, if you do the subtraction, that means in real, like when you remove the log, they will come in division, right? And 0 dB corresponds to the gain of 1. And the other, the gain at gain crossover frequency will come in denominator. So that's why it is 1 by this gain. And since gain crossover frequency, the transfer function was 0, so 1 by 0 will become infinity. So the gain margin is also infinity in this particular case, as well as the gain crossover frequency is also infinity. So the phase crossover frequency and gain margin both are infinity for this particular transfer function. Is this clear to everyone? Did you understand the phase crossover frequency, gain margin, these concepts? See, you can refer to books for formulas, but there is something, the few things that we need to keep in mind for stability, okay? Like few frequencies which are important to us are, one, the frequency where our gain goes below 0 dB. That is gain crossover frequency. Now, since gain is already going below 0 dBs, so what we try to do is we try to calculate the phase at that given frequency. And using that phase, we find phase margin. Okay. Now, when we come to a phase plot, in phase plot, the limit for stability is minus 180 degrees. If your system goes, like your phase goes below minus 180 degrees, the system will be unstable. The reason, should I explain the reason why the limit is 180 degrees, like minus 180 degrees?
Yes, madam. Yes.
Will it be too much?
Please explain.
Okay, so there is a lot to this, but if I talk about it very briefly, for stability, so the idea is, we have this S plane, okay? In S plane, we have real axis, we have imaginary axis. All our poles and zeros that we obtain, all the poles and zeros that we obtain can be fixed in this, right? So the idea is, whatever appears on this side of the plane, left hand side of the plane, these are stable. Stable poles. Because as I already mentioned that we consider stability with respect to poles. So that's why the poles which come on the left hand side of S plane are stable poles. The moment you have poles in right hand side, the system becomes unstable system. Okay. In this also, in left hand side, depending on different poles, how your poles are located, where your poles are located, depending on that, your stability changes. Okay. Whether the system is fully damped, over damped, under damped, or is it marginally stable, it all depends on pole location. So the limit of stability comes at y-axis. Now, when your poles are lying at y-axis, that is the edge of stability, right? So if your poles are at y-axis, that means pole value would be j omega, right? Plus minus j omega. Correct? So it is, so how will your transfer function look like? 1 by s or 1 by s square. Correct? So for a two-pole system, when you have your poles at y-axis, so when you have your poles at y-axis, that means the system is marginally stable. Marginally stable means it is at the edge. So it is not stable but not unstable. So it is at the edge. So that is the limit for stability. Okay. So now if see you have a two-pole system with your poles at y-axis. Poles at y-axis means your real part is 0. Correct? So your two-pole system will look like 1 by s square. Correct? Now if I write the angle or phase of this particular system, how it will look like? Minus 90 degrees, minus 90 degrees. Correct? So this is minus 180 degrees. So if we go beyond this for a two-pole system, if you move right to this particular limit, this system becomes unstable. So that is the reason that for a two-pole system, you have your limit as minus 180 degrees. Or in general, two-pole, and starting from two-pole to all like multi-pole systems, the limit is minus 180 degrees in phase. Okay? Because instability starts from, like, single pole system is never unstable because 180 degrees is the limit, right? If you have single pole, the maximum angle that it can introduce is 90 degrees. You still have a phase margin of 90 degrees, right? So that's why single pole system can never be unstable. In whatever frequency range you operate that particular system, it will never become unstable. But starting from two-pole system to higher pole systems, the system becomes unstable, and that's where you need to calculate these phase margins. So phase margin tells you how much of a phase you are still, you have in hand, like how much of phase value you still have in hand um, um, before you hit the final limit. And more the phase margin, more stable the system is. At a particular frequency, if you compare two systems and corresponding to them their phase margins, the one with higher phase margin will be more stable. Similarly, the case with gain margin, like the higher the margins that you are left with, the more stable the system is. Okay? So, yeah, that is the idea. So, for that is the limit. So we need to keep these limits in mind. For phase, minus 180 degrees is the limit. For gain, 0 dBs is the limit. And the frequencies where these limits are being crossed, in those limits, then we calculate the corresponding other value. Like if phase is crossed, then gain margin. Gain is crossed, then phase margin. That is the idea. Okay? Did you understand that? Any doubt? We can take this in more detail when I'll discuss the stability, that whole concept together. I'll go into more details of all this. But for now, just for understanding purpose, I'll give you a brief insight. Okay? Yeah, moving on to the next problem. In this problem, it is given that A into beta is K upon S plus 2, S plus 1. Find the value of K and omega GC, that is gain crossover frequency. Okay, gain crossover frequency, right? Gain crossover frequency means mod Ts equal to 0, इसका corresponding omega GC, such that the phase margin becomes 270 degrees. Phase margin is 270 degrees. Okay, so phase margin is 180 degrees plus phase at given omega, whatever omega it is. So now for this we have to first write the phase. So phase of this particular system would be phase AB minus tan inverse j omega by 2 minus tan inverse j omega by 1 minus tan inverse j omega by 2 minus tan inverse j omega by 1, right? So here this particular phase need to be substituted to phase margin. Phase margin is 180 degrees minus tan inverse omega GC. At omega GC this will happen. So omega GC by 2 is 270. So now when we cancel out, we get tan inverse 90 degrees or minus 90 equal to tan inverse omega GC plus tan inverse omega GC by 2. So tan inverse A plus tan inverse B, how will we write? This is nothing but trigonometric equation. So tan inverse A plus tan inverse B is tan inverse A plus B by 1 minus AB. Right? So from here, when we calculate, this is 1 by 0 equals omega GC plus omega GC by 2 upon 1 minus omega GC square by 2. So you can equate the denominators, and from there omega GC turns out to be root 2. Now if this is omega GC, then the next step is to find the value of K. Since this is gain crossover frequency, so we know that the gain at omega GC would be 0 dBs. So transfer function was K upon 1 plus S, 2 plus S, right? Yes. So mod Ts is K by root over 1 plus omega GC square 4 plus omega g c square root under equal to 1. So this becomes k square equal to 1 plus omega g c square 4 plus omega g c square. So k square is 1 plus 2 into 4 plus 4 plus 2. So this is 3 into 6. So k is 3 root 2. Yes, so k is 3 root 2 and omega gc is root 2. Gain crossover frequency omega gc. That's why we used this equal to 1. So is this clear? How we solved this problem? First of all, phase margin was given at gain crossover frequency. So we tried to find what is the gain crossover frequency. And we know that at gain crossover frequency, your gain becomes 1 volt by volt or 0 dBs. So that's why we calculated the gain and we equated it with 1. And then when we solved, we got the value of k. Is this clear? Okay, so I hope there are no doubts. Now let's move on to the next problem. So in this problem, consider a feedback amplifier for which the open loop gain A is given as A is given as 1000 by S 1 plus S by 100 1 plus S by 1000 square. Okay, so this is A. If the feedback factor beta is independent of frequencies, so beta is a constant. Okay, if beta is constant, find the frequency at which the phase shift is 180 degrees. Find the frequency at which the phase shift is 180 degrees and find the critical value of beta at which oscillations will commence. Okay, so if beta is constant, then A beta will be having when beta is constant, that means A into beta will not have any effect on the phase. The phase will still come from only A, right? The open loop transfer function. So the phase of A into beta is also equal to the phase of A, which is minus 90 degrees because of S, minus tan inverse S by 100, minus 2 tan inverse S by 1000. So this is the phase. So it is given that find the frequency at which the phase shift is 180 degrees. So phase shift is 180 degrees. That means 180 degrees. If we equate it to 180 degrees, or maybe I can write j omega directly. So this is 270 or minus 270 tan inverse j omega by 100 minus 2 tan inverse j omega by 100. So if we solve this, we can obtain that the omega at which we get this 180 degree phase is 218.22 radians per second. This is the phase that we get after we solve this particular equation. And then what we need to understand is, to start an oscillation, here it is given, find the critical value of beta at which oscillation will commence. So now since beta is constant, so definitely its impact will not be observed in the phase, right? But its impact can be observed in the gain. So that's why we go ahead with the condition of oscillation for gains. That is, A into beta should be greater than equal to 1 for oscillation. So this is the condition for oscillation. For oscillations, A into beta should be greater than 1. So the phase for this is, for the gain for this, how do we write? It is beta by 10,000 omega root under 1 plus omega square by 10 to the power 4 into root under 1 plus omega square by 10 to the power 6 ka whole square should be greater than equal to 1. And here we will substitute this omega. So omega naught, let's say. So I'll write omega naught. So when we substitute it here and we calculate, the value of beta that we will obtain is, beta should come out to be greater than equal to 0.5487. Okay. So this is the value of beta that we need to obtain. We need to use so that we can have sustainable oscillations. Okay. Right. Now coming to this 9th problem. So here the voltage gain of an amplifier with 5% negative feedback is 10. Voltage gain AV is 10 with a voltage gain of an amplifier with 5% negative feedback. 5% negative feedback. That means beta is 5%. That is 5 by 100. So beta is 0.05 is 10. The voltage gain without feedback would be how much? So if this is the voltage gain and this is beta, we know AV is A upon 1 plus beta A. So 10 equal to A by 1 plus 0.05 A. So this is 10 plus 0.5 A equal to A. So 0.5 A is 20. Right? Again, straightforward, very straightforward. Now moving on to this final problem for today. It is about input resistance of ideal voltage amplifier and ideal current amplifier. So what will be the input resistances? Input resistances for ideal voltage amplifier and ideal current amplifier. We discussed this, right? What are the input resistances?
Infinite and zero.
Yes, for voltage amplifier, it would be infinite. For current amplifier, it should be ideally 0. Right? So, yeah. So, these are all the questions that I had for today. And we are done with all the problems. If you have any doubts, you can feel free to ask. Else, we can break over here and meet next week again with new set of problems and concepts.
Thank you, madam. Thank you.
Please go through the lecture once again and also the video. We discussed a lot of things. I believe that few things might not have been absorbed very efficiently. So going through it once again will definitely help. And in case you feel there is some doubt, you can raise that doubt in next session.
Thank you, madam. Thank you.
Thank you. So if nobody has doubt, maybe we can break over here. That's all for today from my side. Any doubts?
Thank you, ma'am.
Okay. Thank you. Then if you don't have doubts, so enjoy your evening. Thank you for joining. Let's meet again next week. Until then, bye.